Now let me start the concept of a displacement current. So this is one thing that comes into Maxwell's equation the minute we move from static to dynamic. Okay, you have not seen displacement current as long as we were talking of static. So for this, I would like you to just go to the Maxwell's equation del cross H is equal to J. Okay, this is the equation in the electrostatic form. And if you remember, this has come from Ampere's law. Okay, now what you do is take this equation and consider take the divergence of this vector on both the sides. What I'm saying is take del dot del cross H, okay, and then the right hand side becomes del dot J. Okay, now you can clearly see that it is a divergence of the curl of a vector. It is a divergence of the curl of a vector, and you know that the divergence of the curl of a vector has to be 0. Therefore, the left hand side becomes 0. Okay. Now, what you do is you're basically trying to take an equation in the electrostatic form, the Ampere's law equation, and apply dynamics to it and apply dynamic conditions to it. Okay, that's what we are trying to do. So first what you do, take the divergence and show that the left hand side is going to be equal to 0. Now come to the right hand side. When you come to the right hand side of the 0 of this equation, you find that del dot J is not going to be equal to 0 in dynamic condition. In static condition, yes, del dot J was equal to 0, but in dynamic condition, del dot J is not equal to 0. How do you know this? We know that the continuity equation says that del dot J should be equal to minus dou rho V by dou T, where rho V is the volume charge density. So, if there is a dynamic situation, then there is a flow of charges and rho V is not a constant. Therefore, the right hand side of the equation is not equal to 0. The left hand side was equal to 0. Which is telling us that you cannot write the equation del cross H is equal to J and use that equation as it is for a dynamic condition. You need to modify it. So how do you modify it? You can modify it in this way. Look at equation 12. Instead of writing del cross H is equal to J, write it as del cross H is equal to J plus JD. Now, what is J? J was the conduction current density. J was the conduction current density. Okay. And now, what is the JD that we have written? Certainly, that is also a current density, but this JD is called the displacement current density. We have introduced a concept called the displacement current to explain dynamic condition or to explain how the Maxwell's equation has to be modified, okay, for dynamic condition. So we have done this. We have written del cross H is equal to J plus JD, where JD is called the displacement current density. Now let us see whether we can apply divergence on both the sides. So what we'll do is, let us call this equation 12 as the modified Ampere's law. Okay, now take this and then take divergence on both the sides. When you take divergence on both sides, what will you get? Del dot del cross H is equal to del dot J plus JD. Del dot J plus JD. You know that del dot J cannot be 0, but there is nothing preventing this from becoming equal to 0. Okay, and let us see what is the outcome. The outcome of del dot J plus JD equal to 0 will be that minus del dot J will be equal to del dot JD. Okay, and you just minutes back have seen that del dot J from continuity equation was del dot J equal to minus dou rho V by dou T. So use that here. When you use that here, you're going to get del dot JD equal to dou rho V by dou T. But at the same time, what I want you to do is use your Gauss law. When you use Gauss law, instead of rho V, you can substitute rho V with del dot D, where D is the displacement vector. Okay, so just put that And then assuming that this medium is homogeneous and it is a linear medium, you can take this del out of your dou by dou t. Therefore, you end up with del dot dou d by dou t. So what did we get? We have got del dot jd equal to del dot dou d by dou t, or you are able to get an expression for this displacement current density. We introduced a concept called displacement current density, and mathematically we are able to see that this displacement current density is dou d by dou t, where capital D is the displacement vector. Okay. Or to summarize what we have done till now, we will write this modified equation. So this modified equation that we have written is del cross H is equal to J plus JD. This is called the modified Maxwell's equation or modified Ampere's law. Okay, and J is the conduction current density and JD is the displacement current density. Now, if you go to the genesis of this particular concept, okay, you can find out what is the significance of this displacement current density. Say where this displacement current density concept will be used means you can explain the propagation of radio waves and television waves through media, through space, okay? Through space using the concept of displacement current density. You cannot use the conduction current density to explain this. You will have to use the concept of displacement current density. And one thing to remember is that at low frequency, the displacement current density can be neglected, whereas at high frequency, so this displacement current density becomes appreciable or cannot be neglected at radio frequencies or at frequencies when your communication systems work. Okay, so in those frequencies, this displacement current density becomes very significant, and J and JD will become comparable. Okay, now I was telling you, we can look at the genesis of the whole thing. If you look at the history of this displacement current density, it came out of the mathematical genius of the Maxwell's equation. So Maxwell really did not come out with any new law. He didn't do that. The already existing 4 laws he took, he put them together, and then, okay, he applied dynamic conditions and then brought in to mathematically, explain that the left hand side and right hand side were equal to 0. He brought in this concept of displacement current density. Okay, and at that time there was no experimental proof for this. He was able to explain propagation of electromagnetic waves using this concept of displacement current density. But at that time, at the time when this man was doing this work, nobody has actually generated radio waves. Source of radio wave was not known. Nobody has generated radio wave or allowed it to propagate or detected radio wave. Okay, yet this idea that JD will be appreciable at those frequencies, those things he was able to, it was a foresight. Okay, and years later, it was actually Hertz who really did the experiment. He actually gave a proof to Maxwell's theories. He was able to generate, he was able to propagate, and he was able to detect radio waves. And this propagation happened in space. And that led to your wireless technology. Okay, wireless communication was born then. Okay, so that's the genius of the work. Now let's just go a little ahead. So till now we have been talking of this displacement current density. So now let's talk about displacement current itself. You know the relationship between current and current density. So from that you're writing ID equal to integral JD dot ds. And we have also seen that JD is dou D by dou T. Okay, now why is this equation important? This equation is important because it's trying to tell you something. So what is it saying? This equation says that whenever there is a time varying electric field, where is electric field here? E is equal to epsilon E. Yes, electric field is there. Whenever there is a time varying electric field, the result will be the displacement current, or the displacement current is a result of time varying electric field. So when we are talking of time varying electric field, we are talking of a dynamic situation. Okay, so only in dynamics this displacement current concept will come. And again, this becomes appreciable only when you're talking of high frequencies. Okay. Next, how do you justify this modification of Ampere's law? How do you justify this? So for that, let us first of all uh, consider two plates of a capacitor. So this is a capacitor, okay, and there is a wire and it is being charged. So it is being charged means the rest of the circuit is not given to you. You are shown a conduction current in the wire I. Here also there is a conduction current I. But then you can clearly see that there is a gap here. Between the plates of the capacitor, there is dielectric, so there is no current. There is no conduction current in that space. Okay. And next what you do is, let us apply your Ampere's law in the non-modified form. In the non-modified form, in the original form, let us apply Ampere's law. So Ampere's law, where are you going to apply? You're going to apply it through this wire, through this current carrying wire. You have your Amperian loop indicated by that blue loop, and the surface, okay, enclosing this loop is, or the surface enclosed by the loop is S1. Let it be a flat surface S1, and then this is your loop. Okay. Now you apply H dot dl to that. When you apply H dot dl to that, then the right hand side will be the current I enclosed. And what is current I enclosed by this Amperian loop? That is your current through the wire, the conduction current through the wire. Okay. And the right hand side of the equation also can be obtained from applying this J dot integral J dot ds to the surface S1, that is to this blue surface. Okay. Then you're getting the right hand side to be I, which is the conduction current. Next, what you do is, at the same spot, you take your Amperian loop, but now what you're going to do is, the surface which is enclosed by the Amperian loop, you stretch it. So it was initially like this, next you stretch it, okay? You stretch it so that it is able to enclose one of the plates. It is able to enclose one of the plates, okay? Now you apply Ampere's law, meaning you're going to apply Ampere's law to surface 2. When you apply it to surface 2, the left hand side definitely is not changing. It's the same for S1 and for S2. The left hand side is integral H dot dl over the loop L, so that is not changing. But come to the right hand side. When you apply it to the second surface S2, you find that the right hand side will be 0. Why is it going to be 0? Because no current is cutting through this surface. No current is cutting through the surface S2. So the right hand side is 0. So you are clearly seeing a discrepancy in the situation, okay, when you are applying your non-modified original Ampere's law. Okay. Now, how do you rectify this anomaly? So for that, we will modify Ampere's law. When you modify Ampere's law, you will write the left-hand side as integral H dot dl, and the right-hand side, you are now going to not just leave it as J dot ds. We had modified and written J plus JD, remember, so it will be integral J dot ds plus integral JD dot ds. Okay, and how are we going to explain it to this particular problem? So here you have your capacitor plate and then you have this. So how we do that is, when you apply it to surface 1, then only this part remains. Okay, and when you apply it to surface 2, this is surface 1. When you apply it to surface 2, then only this part remains and this becomes 0. So one is 0 when the other is non-zero. Okay, so that's what is written here. It is J is 0 for surface S2 and JD is 0 for surface S1. Okay, therefore you can look at this equation. It is H dot dl is equal to integral JD dot ds if you are applying it to S2. Okay, and that is equal to d by dt of integral d dot ds. How do you get this? because you know JD is equal to dou D by dou T. Okay, and you just look at this d by dt of integral d dot ds. So from amperes, from your Gauss law, integral d dot ds is after all your charge only. It is simply your charge enclosed. It is charge enclosed. Therefore, when you take the time differential of it, it is going to be dq by dt. And what is dq by dt? dq by dt is I. dq by dt is I. And where have you applied it? You have applied it to surface 2. So that means between the plates of the capacitor, you are talking about a current called displacement current. And this displacement current is equal to the conduction current in the conductor. So when you're talking about the conductor, it is a conduction current, and in the dielectric part of it, it is as if, you know, it is like there is a continuous flow of charge, and that charge flow in the dielectric, you call that as the displacement current. And from the continuity of charges or for conservation of charges, you get ID equal to I. Okay, and please, this is very, very important. JD is not equal to J. It is ID equal to I. But del dot JD equal to minus del dot J. Okay. Okay, then the next few slides are basically a conclusion of this chapter, of this concept. You can just go through it yourself. Okay, now finally, I've given you the generalized form of Maxwell's equation. You can see that these 4 equations which are written here are the equations for dynamics. And you can see that both these equations, first 2 equations, do not change in static condition and in dynamic condition. That is Gauss law for electrostatics and Gauss law for magnetism. Both of them remain the same even when we come to dynamics. But then there are 2 curl equations that you are having. The 2 curl equations that you have will get modified. Look at this. Here del cross E was equal to 0 when you were talking of statics. But it has become del cross E is equal to minus dou B by dou T, and it is Faraday's law, and the implication is that changing magnetic field gives rise to electric fields. So one gives rise to another. Change in one gives rise to the other. So they are no longer independent. Now let's come to the 4th equation, which is Ampere's circuit law. So here also you're saying that initially the original Ampere's law was del cross H is equal to J. But now it's got modified. It is J plus JD. It is actually J plus JD, where JD is dou D by dou T. Okay, so this is the extra thing that has come, the concept of displacement current. And what is the implication of this? The implication of this equation is that changing electric field gives rise to magnetic field. So again, this equation talks about the interrelationship between electric field and magnetic field in dynamic conditions. Okay, so when somebody asks you Maxwell's equation, you should be able to write Maxwell's equation in static situation, both integral and differential form. Similarly, once you're talking of dynamics, you should be able to write Maxwell's equation for dynamic situation, both in terms of differential form and the integral form. Okay. Now, once we are done with it, we will go to a new share. I'll do one thing, I'll just stop sharing and I'll take a new share. Okay, so this is going to be my new slide. It is 9b. Okay, but straight away I will go to summarizing. Okay, what is the difference between statics and dynamics? So summary of all the equations. So the first thing is Lorentz force equation. Lorentz force equation is associated with Maxwell's equation because after all the concept of electric field and force relationship comes from here only. Remains the same for statics and for dynamics. Next, let us come to the continuity equation. By now, you must have realized that continuity equation is implicit in Maxwell's equation. Just now we have seen, we have used this concept of continuity equation to rewrite Maxwell's equation. So it is implicit. Then once these two are over, let's go to the concept of linearity, isotropy, and homogeneity. These three things are after all properties of medium, material medium. Therefore, they apply to time varying fields also. Same for both dynamic and for static conditions. Once we are done with that, let us go to the three equations called constitutive relations. Okay, we'll go to three equations called constitutive relations. They are called constitutive relations because these three, they are called constitutive relationships because these three quantities, sigma, mu, and epsilon, these three factors or the values of these three define the property of any material medium. Sigma, you're going to see as we go along, every problem, these three will be given. And these three are called the constitutive parameters. They are called constitutive parameters. And the value of these constitutive parameters will tell you something about whether the medium is a dielectric or a conductor or let's say free space. Okay, like for example, for free space, I'll tell you sigma will be 0, no conduction. Mu will be mu naught. Epsilon will be epsilon naught. So basically, these three are called the constitutive parameters. And where do you come across these constitutive parameters? They are seen in these three equations, 16, 17, and 18. I'm not going to get into it because it's only a summary. Okay, and therefore, these three equations are called constitutive equations. And these three equations we have seen in the introductory chapters for statics. They hold good even here for dynamics. Then, if you remember in statics, we had written two equations for boundary conditions in magnetism and two equations for boundary conditions in electrostatics. All the four equations are going to be valid for statics also. Okay, I'm not going to get into it because we have discussed these things at length. And similarly, when we wrote these boundary conditions for a conductor also, we had written the boundary condition. That also holds good. Okay, next, let us go to the other equations. Now, when you go to del dot B equal to 0, it's a Maxwell's equation. You can clearly see it's Maxwell's equation. So del dot B equal to 0, del cross E equal to minus dou B by dou T. Both these equations are called the compatibility equations. And B is equal to mu H and D is equal to epsilon E because they were written in another form in the previous thing. B was written as mu naught H plus M and all that. Okay, and D is equal to epsilon naught E plus P. Okay, so these two equations are also called the constitutive equation. Basically, they are the same equations as you have seen in the previous slide. And then what you are left with will be two other Maxwell's equations. Now, these two are called equilibrium equations. Okay. Now from here, let us go to a concept that we have studied in our statics. If you recall, we talked about something called the scalar potential and the vector potential, if you remember. Okay. Now the concept of scalar potential and vector potential and how you relate vector potential to current density J and scalar potential V to the volume charge density holds good for static condition. So we're leaving it there. And let us see how fields were written in terms of scalar and vector potential there. If you remember, since del dot B equal to 0, it's a basic Maxwell's equation. Since del dot B equal to 0 for both static and for dynamic, the equation B is equal to del cross A, where A is the vector potential. B is equal to del cross A, which we had used in statics, holds good here. It holds good for both statics, static situation, and for dynamic. Okay, holds good for both. Okay, now what we are going to do is, let us take the next equation. See, this del cross E is equal to minus dou B by dou T. Where is that? Del cross E is equal to. So basically we are looking at the compatibility equations. Now you must be getting some idea why we are calling them as compatibility equation. We took the first compatibility equation and said that it is compatible to both dynamics and for statics. Okay, so let's take the next compatibility equation. Taking the next compatibility equation, okay, del cross E is equal to minus dou B by dou T. So here what we will do is, let us substitute B is equal to del cross A. Okay, when you do that, what are you going to get? You can see that there is a curl here. There is a curl involved on this side also. Okay, or you can write this as minus of del cross dou A by dou T. Okay, now using this, bring the right hand side also to the left hand side. So it becomes del cross E plus dou A by dou T equal to 0. E plus dou A by dou T. Curl of E plus dou A by dou T equal to 0. Okay, now when you are getting a curl of any vector as 0, the curl of any vector is 0, then mathematics will tell you that it is possible to write that vector. You can write that vector as a negative gradient of a scalar function. If del cross, if the curl of any vector, let us say some vector, what symbol shall I use? Z. If curl of any vector is 0, then that vector can be written as negative, okay, negative gradient of some scalar. Have we seen this before? We have seen this before, and this is something that we have used for static electric field. Del cross E equal to 0, therefore E equal to minus del V. We wrote in statics. Okay, so the same idea we are going to borrow here also. Only thing is, because it is dynamics, it is not just E, it is E plus dou A by dou T. So this E plus dou A by dt, we will write it as minus del V, where V is the scalar potential. Or we can now get an expression for E. E is equal to minus del V minus dou A by dou T. Okay, so what did we have? B equal to del cross A was one equation. The other equation we have is E equal to minus del V minus dou A by dou T. Now, if you look at this equation, this is true for both dynamic and for static. But when you come to equation 23b for electric field, this equation was E is equal to minus del V for statics. But when it came to dynamics, it is E equal to minus del V minus dou A by dou T. Okay. And both these equations, if you remember, have, yes, the starting point was the compatibility equations. Okay. Now you have got how to write the two fields in terms of scalar and vector potential. Scalar potential is V and vector potential is A. So next what we are going to do is we are going to write Maxwell's equation in terms of scalar and vector potentials. You know the four equations which were written either in terms of H, E, B or D. Okay. So these equations we are now going to write in terms of scalar and vector potential. Let's start off with the first equation, which is your Gauss law. Del dot D is equal to rho V. Take this equation, and what we need to do here is, you know that D is equal to epsilon E. Use that. When you use that, you will get del dot E equal to rho V by epsilon. Okay, next, take divergence on both sides of this equation. Okay, when you take divergence on both sides of the equation, not only taking divergence, also substitute for E. E is after all minus del V minus dou A by dou T. Make that substitution also and take divergence on both sides. Okay, so I'm sorry. I'm sorry. You don't have to take divergence on both sides. I'm sorry. I'm sorry. I wrote something stupid here. Already there is a divergence. Del dot E is equal to rho by epsilon. Rho by epsilon. Only thing you're doing is substitute for E. Substitute for E. When you substitute for E in terms of minus del V minus dou A by dt, let us see what we are getting. So expand this. So when you expand this, you're getting minus del square V minus dou by dou T of del dot A is equal to rho V by epsilon. Or take multiply left hand side and right hand side by minus 1. So you get del square V plus dou by dou T of del dot A equal to minus rho by epsilon. So this is your Maxwell's equation, no longer in terms of electric field. It is written in terms of scalar and vector potential. Okay, next. Let us now go to the next Maxwell's equation. The next Maxwell's equation is modified Ampere's law. Take that equation. Del cross H is equal to J plus JD. So instead of JD, put dou D by dou T. Okay. And you know that B is equal to mu H. B is equal to mu H. Therefore, del cross B will become equal to, that is multiplying the left hand side and right hand side with mu, will give you del cross B on the left hand side, and on the right hand side mu into J plus dou by dou T of epsilon E. So D is equal to epsilon E, we have just used that here. Okay. Next, what you do is, you can substitute for B. Substitute for B. So when you substitute for B, what happens? B is del cross A. So you get del cross A. And what is del cross A? Del cross A will become del of del dot A minus del cross A, and come to the right hand side. On the right hand side also do the same exercise. You write mu j, open the bracket, mu j is the first term. When it comes to second term, you will have mu into epsilon dou E by dou T. But only thing is, don't keep it as E, because our aim is to write everything in terms of scalar and vector potential. So write dou by dou T of minus del V minus dou A by dou T instead of electric field. Right? Nothing, you're not done anything. You simply took your modified Ampere's law, okay, and rewrote it in terms of B vector and E vector, and then substituted B is equal to del dot A and substituted E equal to minus del V minus dou A by dou T. That's it. Once more I repeat, you start with the modified Maxwell's equation, which will be in the form of H and D. Write it in the form of B and E, and then substitute B is equal to del cross A, and substitute E equal to minus del V minus dou A by dou T, and simplify. Okay. Once you do this, you're going to get equation number 24B. Okay, so this is your Maxwell's equation when you're going to write it in terms of scalar and vector potential. And there is additionally J also. Quite a complicated looking equation. Very complicated looking equation. So now we are going to do something to make it simple and elegant. Okay, so let's see what we are going to do. So you all know that a vector field can be uniquely defined only when both the curl and divergence are specified. This comes from mathematics. A vector field is uniquely defined only when both the curl and the divergence are specified. Okay, so have we specified the curl? Yes, we have already specified the curl. B is equal to del cross A. It's already specified. Now let us attempt to do the same for divergence also. So for the vector A, let us write divergence. Del dot A, let us assume it is equal to minus mu epsilon dou V by dou T. Okay. So now we are specifying it in this form. Now you may wonder, why are we doing it this way? Now specifying del dot A as minus mu epsilon dou V by dou T, this is called Lorentz condition for potentials. Okay, writing it this way is called Lorentz condition for potentials. And why have we taken the divergence of the vector potential this way will be explained once we go to the next slide. Okay, now, so what was Lorentz condition? Lorentz condition is del dot A equal to minus mu epsilon dou V by dou T. Now what you're going to do is take this Lorentz condition, put it in the two Maxwell's equation that you got. First Maxwell's equation you wrote in terms of potentials was Gauss law. The second one was modified Ampere's law. So both those equations that you got, into them put your Lorentz condition. Okay. So what is the Lorentz condition? Instead of del dot A, you have to write minus mu epsilon dou V by dou T. Maybe I'll just go back and show you. Instead of del dot A, you have to make that substitution. Make that substitution and then simplify the equation. Similarly, do the same for the Gauss law also. Once you do that and simplify, okay, the mathematics I don't want to waste my time doing. If you do that, you're going to get this equation for Gauss law and this equation for the Ampere's law will get modified and you will get this. Or in other words, you are looking at equation 25A. If you look at 25A, you're seeing that it is a pure equation involving only the vector scalar potential V. It just involves the scalar potential V, and on the right hand side you have charge. Okay, and if you look at Ampere's law, modified Ampere's law now, after applying this condition, Lorentz condition, you are getting a pure equation in terms of the vector potential A, and on the right hand side you have J, current source, whereas there you have charge source. Okay, or if before applying this condition, let us go to both those equations and see. You're seeing that this equation involves both A and V, and it didn't look elegant at all. Okay, similarly this also, you see V and A were there. Now by applying this Lorentz equation, you have modified those two equations into two equations which are very, very symmetric. The first equation has the charge source on the right hand side, that's not changing. The second equation has the current source on the right hand side in Ampere's law, that is also not changing. But you are now able to write two equations which quite resembles your Poisson's equation. So the first is called the scalar Poisson equation, and the second equation is called the vector Poisson equation. Only thing is there is also a second derivative of time involved. That's not unexpected, because after all here you have x, y, z and time dependence. Okay, so now you got the answer to why we suddenly out of the blue we had taken some equation called Lorentz condition. So the Lorentz condition for potential was chosen to uncouple the two Maxwell's equation written in terms of potentials A and V. Okay, and write them as two symmetric equations. And these two equations are also called wave equations 1 and 2. Okay, so a complicated, unelegant set of equations now got converted into two equations which are very elegant, which are quite your Poisson's equation in the vector and scalar form. Okay, and now they represent Gauss law and your modified Ampere's law after you have put the Lorentz condition. Okay, now these equations we have applied to dynamic conditions. Okay, so now if you have to rewrite this in statics, what will happen? Time dependence is simply not going to be there. So what will happen? Look at this equation 26a and b. 26a and b. So you will have del square v is equal to minus rho v by epsilon, and del square a is equal to minus mu v. These are the two special static wave equation 1 and 2. So now you see how beautifully from the dynamics you are able to get your static equation quite simply. Okay, now these are two wave equations. So obviously there will be some solution also to this. The solution for equation 25a will be getting what is b. Similarly, equation 25b, it will be getting what is a vector. Okay, let's see that in the next slide. So directly we are giving you the solution. You are having v and you are having. So where am I? Where am I? Where am I? Where am I? One sec. I have gone somewhere. Okay, so yeah, so what we have here, no, I am missing something. Oh, wait. Let's go to this. Something's gone wrong. One sec. Sorry. So let's go to 10. No, don't tell me. Don't tell me. I'm going to miss all this talking. Okay, or what I'll do is, I'll straight away. It's not drawing that I want. So what do I do now? Okay, let me forget all this. Go straight away. So you have your B vector. You can see your scalar potential is written as integral rho v dv by 4 pi epsilon naught epsilon r. Now if you see the static, you won't find this square bracket. You won't find the square bracket. So that means the square bracket is having a significance. The square bracket is having some kind of a significance. What is the significance of the square bracket? Let us see. So the square bracket rho v you are having. Similarly here you are having square bracket j. Okay, J is a current source and here rho is the electric field source. Okay, and J is actually the source for magnetic field. Now, what do these things mean? This rho v and J, its square bracket means that T in the term rho is a function of x, y, z, t, and J as a function of x, y, z, t is replaced by what is called the retarded time T prime is equal to T minus R by U. Read this again. So these are retarded potentials. These are no longer your normal potentials that you have seen in your static. Now these are retarded potentials, and the retarded potential, what happens is you are going to talk about a time which is not the time you're observing the field. You're talking about a time before that. You're talking about a time T prime is equal to T minus R by U, where R is the distance between the source of the field and the observation point of the field. Your electric field, for example, has a charge density rho. That's a source. That is at some point. Okay, you are observing the field at some other point. And you're talking about the distance between these two. And you're talking about a time that you're talking about a time when, okay, the field configuration, you're talking about a time t, and at the time t, your charge configuration would have already changed. So you're talking about a time t prime, which was before that, which gave rise to the field at this point. I'm repeating again, I'm talking about a field at a time t here, which was created out of a charge configuration at a time t prime, which is t minus r by u before the field information got there. Okay, and what is u? U is the speed or the velocity of propagation. Or in other words, now we are no longer presuming that action at a distance. At action at a distance, we always talked about waves traveling at the speed of light. So if something happens here at a time, then at this point, the effect is instantly felt. That's what you studied in physics. Okay, but when you're coming to dynamics, you cannot do that, it says. It says that you have to consider these two times separately. At a time t, you're talking about a field here, which was created by a field child charge configuration at a time t prime. T prime. Okay. After that, because of dynamic situation, this charge configuration could have got changed. And this E here is not because of the current charge configuration. It is because of a charge configuration at a time t prime. Or you're talking about a retarded situation. So that's why it's called the retarded field. Okay, and this becomes, these ideas of retarded potentials become very, very significant when you are talking about communication. Okay, like, so let's just read what it says. So retarded potentials for electromagnetic fields are generated by time varying charge distributions or currents of the past. Okay, so you have to consider that small time difference also, because quickly things are changing. So the fields propagate at the speed of light. So the delay of fields connecting the cause and the effect at earlier and later time is important. So that's the big difference. Okay, the signal takes a finite time to propagate from a point in the source to another point where we are observing it. So this time lag has to be considered. So that's the reason why you are considering the retarded configurations. Okay, and you're talking about these as retarded potentials. Is it fine? Okay, and why are we talking about scalar and potential, scalar potential and vector potential? The scalar and vector potentials simplify calculations of fields. Okay, they create a symmetry. You've already seen there is a certain symmetry between the vector and scalar potentials. They create a symmetry, and therefore they become very useful in antenna field calculations. So what is done here is the field values are first obtained. The source values are obtained, and from the the source values are first obtained. From the sources, you are able to get your V and A, and from V and A, you're going to be able to get your fields. So that's the way calculation is done. Okay. I know it's Greek and Latin correct right now, but then when you go to those subjects, it will make sense. Finally, to wind up, I will talk about time harmonic fields. Okay, these are not really very difficult and all that. Basically, it's a representation of how you write fields. Okay, normally electric field and magnetic field are written as a function of x, y, z and time. X, Y, Z and time. So this is time harmonic representation. Okay, it's a time harmonic representation. What is harmonic? Harmonic is something that is repeating with time. So a sinusoidal representation, or instead of saying time harmonic, I'll say it is a sinusoidal variation. If you talk about electric field or magnetic field, okay, E and H, you will find that in these waves, they will be varying sinusoidally. Okay, that's the reason why you will write a cosine equation or sine equation to represent these waves. Okay, and there will be a function of both position and time. This is the harmonic representation. But sometimes what happens is, and then again you will ask me, ma'am, should all the waves be sinusoidal? Okay, all waves need not be sinusoidal, but for any wave you can do Fourier transform techniques you can use, and then any waveform can be, or any signal can be actually broken up into a number of sinusoidal waves. which when superimposed will give you the original signal. So that's the significance of the sinusoidal representations. Okay, but sometimes what happens is it becomes nice for us to go for what is called the phasor representation. So what is a phasor? A phasor Z is written as x plus jy, okay, or you can write it as R5 form. This is something like, complex representation and then writing it in the R theta form, something similar. So here you will write R5 form, where if you expand it, it becomes R cos phi plus J sin phi, or you're talking about a complex plane. What is R? R is equal to x square plus y square under root, and phi is equal to tan inverse of y by z. So let's represent it on a scale. So this becomes the real axis or your x, and this is the imaginary axis or your y on the complex plane. Okay, and this is your R. This is your R, making an angle phi with the real axis. Okay, so this is normally something that you have seen, conversion of xy coordinate system to polar coordinate system. You have seen it. The only difference now when we are talking of waves is going to be omega will be involved. There is an omega involved. This vector is not a stationary vector. This vector is going to be a rotating vector. This vector is going to be a rotating vector. So imagine this vector rotating with an angular frequency omega. If it rotates with an angular frequency omega, your phi is going to be, phi is going to be some omega t plus some phi naught, where phi naught was the initial angle at a time t equal to 0. Okay, so we will use the concept of rotating vectors. Rotating vectors are phases. So we will use this concept to write wave equations. Okay. And before we go ahead, okay, this you will understand only when we start working out problems, which we will not do in this chapter. We will do in subsequent chapters. Okay, so next thing is, how do you operate on these phases? So how do you add or subtract phases? Then how do you multiply phases? How do you divide phases? How do you take the square root of a phasor? How do you get a complex conjugate of a phasor? All these things are written here. And I just told you, it becomes a phasor. A vector becomes a rotating vector or a phasor when phi becomes omega t plus a constant. Okay, and look at this. Z is R cos, it's not phi anymore, R cos omega t plus theta plus J sin omega t plus theta. Now you see this. This can be written as R into, you can separate out the angular part and the omega t part and write it as e to the power of j omega t and e to the power of j theta. Right? So now, how do we use this? I will tell you. So a quantity represented as a phasor. Okay, whenever you are representing any vector or a scalar as a phasor, okay, there will be a subscript s put there. When you see the subscript s, you know that it is a phasor representation. So let us see how phasor representation works. So you have your normal representation. Vector A is some a naught cos omega t minus beta x along the ay cap direction. Now this is a cosine function. A cosine function can be written as a real part of an exponential. You know this. Cos theta plus j sin theta. So you can write it as a real part of an exponential. So you write it as real part of a naught. Then you can write it as e to the power of j beta x and e to the power of j omega t. Because the minute you are writing it as e to the power of minus j into omega t, omega t minus beta x, when you're writing it, you can actually divide it, write them as a product of two parts. You can write them as two parts. You can write it as e to the power of minus j beta x and e to the power of j omega t. So that's what has been done here. Okay. Or in other words, you can write this cosine function as a real part of this, or you can write it as real part of a phasor into the time part e to the power of j omega t. So this AS is the phasor representation, where AS is A naught e to the power of minus j beta x. Or you can see that in a phasor representation, it will be a function of only position. There is no time involved. Time has been separated out. Okay. Now, let us look at how do you do the first time differential of A. Okay, when you do that, it becomes, j omega, because you have this e to the power of j omega t. So it becomes j omega as. Similarly, integral a dt will become as divided by j omega, or minus j as by omega. Okay, now this phasor representation can be used to write your from your time harmonic Maxwell equation to the phasor representation. You can write wherever you had dou b by dou t. Okay, you will write j omega bs. Similarly, wherever you had an integral, you will write divided by j omega. So you are expected to know this. Right now, you're not going to use it, but then you are going to require this representation in some of the chapters ahead. Okay, so we are just putting it before you right now. Okay, so with this, I should actually be closing the theory of this particular chapter. And now what we have to next to do is solving problems. So I will stop my recording.